All right, good afternoon. Let's start the lecture. Okay, so we're gonna shift our attention to a slightly different direction now, actually. So previous lectures we have been doing is, basically have a difference. You have a discrete sequence number, and you derive pulse transfer function for either open loop or pulse or a closed loop, right? And then you can design a simple PID control, digital PID control around this basically pulse transfer function or around this data sample system. So today we're going to shift our perspective. Basically, we're going to look at another perspective designing digital controller, which is to use so-called state variable method here. Okay, so it's essentially the model we're using now is we're going to end up with a so-called state space model. Okay, so that's a quite different perspective from the traditional pulse transfer function point of view here. Okay, yeah. So basically, see previously. Maybe I'll just write here. What you design is you have a digital controller at here, and the zero order hold, and your plant. Okay. So basically, this D of Z, you can design it, right? It's designed around. Okay, these two can be converted into one G of Z, can be designed around this G of Z here. So now we're trying to have a difference. How do I come up with a D of Z? Instead of focusing on this G of Z, okay, we're going to transform this G of Z into a state space model. So basically, the objective now, okay, so we're going to transform this G of Z into the so-called state space model. Okay, yeah. And then design digital control. Okay, digital controller around this state space model. So basically, it's a philosophically speaking. Basically, when you're dealing with something, there's one perspective. You deal with this, and you come with a solution, right? And now, what we're trying to do is let's transform this one to a different format. It looks different now, right? And then you deal with this new format, and you come with another completely different type of solution here. Okay. Of course, the objective is the same. You want to control the system. So that's the point here. So we're going to look at this so-called state space model mainly. So let's talk about a little bit about the general concept, basically state variable method. Okay, let's talk about it a little bit general. First of all, what's the general concept here? Okay, and if you have taken monitoring control here, so this will be probably not quite new to you. Okay. Should be fairly okay, but remember, where we're focusing right now is on discrete system. So the terminology may be the same, but it's all about the digital system now. Okay, discrete system. Okay, so let's say we have a system. Okay. And it's all about how you describe the system, right? Describing the system could be as simple as you have one input and two input, one input, one output, and then you use a Laplace transfer function to describe system. Or in our case, for digital system, we use a pulse transfer function to describe the system, right? But now there's another way of describing system. Basically, is to pick a so-called state variables, to use a set of state variables here, right? And these state variables here could be typically we use, let's say, x1 to xn of k here. Okay. So you pick a number of variables, and which we call that state variables. Okay? And it's not arbitrarily chosen often in time. Okay? You know, like mechanical, when you have a mass spin damper system, and the two states you choose, position and velocity. Right? You choose these two states to describe the system. So mathematically, you can pick basically a number of states that are here, and that describe this, trying to describe system. And for the system in general, okay, you could have not just one input, you could have a number of input here. So in this case, I wrote it down here. I have there are number of inputs. Okay. So R number of inputs, and of course you could have more than one output. There's y1 of k to yp of k. So there are p number of outputs. Okay. Yeah. So, and then what I'm giving it here is there are n number of state variables. Okay. So that's a typical mathematical model for a system. Okay. And this is a general system here because we have a multi-input and we have also multi-outputs here. Okay. So we call it MIMO, so MIMO system. Okay. And this is a general because if your R equal to 1 and P equal to 1, then this system becomes basically a single input, single output, which is a SISO system, right? So, okay, yeah. So that's the model in this particular case we're going to use to describe our system. Remember the objective, right? The objective is I'm not going to use a pulse transfer function at here anymore for the G of Z. Basically, I'm not going to design my controller using G of Z anymore. I'm going to transform this G of Z into a different mathematical model. Okay, it's not arbitrary transform. There's also procedures to follow. And then with this state space model, which is basically the idea here. So you have a number of states, okay, and number input output, and then we can design our controller here. Okay, yeah. So let's go back to the state variable here. Okay. So what exactly the state variables mathematically? Now the state variables, it represents the so-called minimum amount of information to determine both the future states and the system output for given input functions. So I'm writing down in it here because I think this is important concept actually. Okay, yeah. You know, we often talk about state variables, talk about state space models, but what exactly does state variable means at it here, right? Yeah. So the keywords here is actually there's the keywords minimum, okay, and the other one is determine both the future state and the system outputs for given input functions here. Okay. So the point basically is, you know, essentially the point here is, okay, so you have a system. How many states should we pick, right? Should we pick 1 or should we pick 2 or should we pick 3 basically, okay? Yeah. And why is it that you pick this number essentially, okay? Yeah. So the idea here is, okay, you don't pick too many, okay? Or you don't pick a redundant number of state variables. You only pick the minimum. Like the mass spin damper system, you know, you have a mechanical mass spin damper system, and then you have the equations for example, for the system, right? Yeah. And the point here is, okay, I will have an input and I have the output x of t here, and I want to know basically what the output is given certain inputs here, right? And I also want to know what the future of this output is essentially, okay, given the input here. So if you want to use state space model to describe this system here, we have to pick the so-called minimum amount. And the minimum amount here, basically you get one is position and the other is velocity. These two will constitute the minimum. And you don't need any more. Or if it's less than that, then you can't describe the system. Right? So these two together is enough. Okay, they're enough to basically describe the system. Okay, and we'll look at it, of course, later. Okay, in terms of state space model to describe system and to determine both the future states and the system output for given input functions. Okay, yeah. So that's the point minimum. And sometimes you picked a number of state variables actually more than the minimum number, then you actually have this so-called redundancy in the system here, in the mathematical model there. Okay, yeah. So in MATLAB there is also a function called minimum realization type of function. So if you have let's say if you come up with a state space model, and if you give it to the MATLAB function, it actually will be able to determine whether the model that you picked has this so-called minimum characteristic there. Okay, yeah. So this is an important one here. We'll probably look at this a little bit later, but for now, just remember that this number of state variable that you pick, okay, needs to be minimum. So because of the nature of the state space model and the description of this system will have a very close connection with the linear algebra. Okay, so basically we use linear algebra here heavily in terms of the state space method here. Okay, so if I have an input, then we define an input vector at here, and you basically form an input vector. Okay, here the vectors are all column vector here, and we're talking about a basically real system. Okay, so all of the components in the vector at here, they're all real. So basically this symbol here basically means this is the real vector with r/1 size. Okay, so that's what it means. Okay. Mathematically, sometimes you can have a complex vector, C. So this is basically meaning r/1 is a column vector here. Okay, and we have output vector here. So y1 of k to yp of k, and that's also real at here. So this is a p/1 vector at here. And of course you can have the state vector. So this is basically the vector representing the state variables, and we use x of k. So whenever you see an arrow signs on the top of the symbol, basically representing a vector in this class. So we have n number of states at here. Okay. So that's Rn/1. Okay. So here is basically the information that you need to describe a system. So what's the model then, right? So in general, the state space model, okay, or equation, is in this format here. So you have x of k plus 1, which is a function of the state variable and the input vector. Okay, so the output, basically the next state, right, is a function of the previous state or the current state and the control input to the system. Try to relate to basically your continuous system. Then the continuous system, this side here is what, x dot, right? Yeah. And then your output here, okay, is also a function of input, okay, and also the function state variable. So this is your general state space model. This basically means it could be linear, it could be nonlinear at here. So this f and g, right? So they're just a function symbol here. Now, of course, what we're dealing with, we're always talking about LTI system. LTI representing what's the name of LTI? That's right? So a linear time invariant system. So we simplify quite a bit, and then the state space model in this case, okay, instead of using f, so we have a linear system now. Okay. So this is the model, linear system model, linear time invariant system model for state space representation here. Okay. Yeah. Now, if you look at this model right here, there are a number of things. Basically, you have to be very familiar with why is it LTI. First of all, this is a linear format, and this A, B, C, D at here, there are 4 matrices. So this A, B, C, D at here, these are called system matrices. Okay, system matrices here. Why is it called a time invariant? Basically, the A, B, C, D here, they are not basically time variant. So they are time invariant, and they are constant. I should probably put it here, constant. Okay. So constant system matrices. Yeah. Good. And because they're constant, that's why this is a time invariant system. The size of A, B, C, D, this is also a very important thing. Because of linear algebra, so whenever you use matrix multiplied by a vector or by another matrix, the size has to conform with each other, right? So x of k, I listed it here. Now this is our n by 1 column vector, and this is your output and an input at here. So that A, B, C, D, right, has to have appropriate size at here in order to give you the right multiplication. So A at here is a n by n size matrix, and B at here, okay, B is something times U, which is a r by 1 here. So this is going to need to be n by r, right? So n by r times r by 1 give you n by 1, which is the same size as this x of k, which is n by 1. Okay? Yeah. And C at here is a p by n vector matrix. So p by n times n by 1, and you get a p by 1, which is the same as y of k output. And D at here typically we call a feed-forward matrix, and often in time a D in our case will actually be just a 0. Okay, yeah, often in time D is 0, but for general description we'll just keep the D at here. So D will be P by R. Okay. So this is your size of the system matrices at here. Okay, so they need to be consistent in order to be able to carry out the multiplications. If your system is a single input, single output, then you could just replace the R, right, with 1, replace the P with 1, so then you get your single input, single output system here. Okay. So the question here, okay, the question here is how to obtain, okay, this discrete state space model. Okay, how to obtain this discrete state space model. So back to my initial objective, essentially. See here, I said here's here's our previous focus, and now we want to transform this G of Z into a discrete space model. So this is basically the question here. How do we obtain this discrete state space model at here? Okay. So basically, So this is your G of Z right here. Okay. So this discrete space model for G of Z, right? Or for these two blocks. Okay. Okay. I'm going to draw a diagram here. This is basically we're going to follow it here. Okay. Here, let's start from the continuous system model. Okay. So here's your continuous system model G of S, right? And then its continuous state model, maybe it's described by ordinary differential equation, right? Like the mass spin damper over here. So this is an ordinary differential equation, right? Yeah. So, and now we're trying to design a digital controller of this, and of course there should be a zero order hold. And the point here is, how do I obtain this discrete state space model for this simple portion, the block at here? There are two approaches you can take. Okay, there are two approaches. The first approach is you start with this G of Z at here. Okay, start with the G of start with the G of S at here. Okay, so this is your continuous system here, right? And then from here, okay, what you can do is we can make use of knowledge that we learned from previous lecture. I will convert this G of S into G of Z by considering a zero order hold in front of it. Okay? Yeah. So basically this portion in here, so get to basically obtain a zero order hold equivalent Z transfer function. Okay, G of Z. Maybe I just make this box a little bit bigger. Okay, so we learned this how to do this. You know, this portion in here, basically, you're doing Z transform, then 1 minus E of TS over S, and then G of S, which is 1 minus Z to the power negative 1, and Z G of S over S, right? That's basically what this step is about. Okay. And once you get this G of Z now, okay, once you get the G of Z, there are two ways. So you can actually directly, we'll show you how to do that next. Okay, you can directly from here to obtain, to derive this discrete state space model. Okay, so once we get the G of Z, we'll be able to derive the discrete state space model. Okay, yeah. Or you could also do is one more extra step at here. So from the G of Z, okay, which is the pulse trans function, to derive this difference equation. Okay, this difference equation. From the difference equation, and then you can obtain this discrete state space model. Okay, so I'll show you both approach shortly. Okay. So always try to remember, compare with the continuous system. In continuous system, when you have a Laplace transform, you can derive the differential equation, right? From differential equation, you can derive the state space model. Okay, yeah. So that's the first branch. Okay, that's the first branch here. So from G of S to G of Z, and then ultimately to the state space model. Now the second branch here is when you have the G of S here, starting from continuous system model or the ordinary differential equation. Okay, then what we can do is we can derive, based on this information, we can derive the continuous state space model. Okay, we can derive continuous state space model. I'll show you a couple of examples when we do. I'll show you in one approach basically how to derive. But this is not our focus here. Okay, So from here to here is not our focus. This is actually sort of an intermediate step at here. Okay. And once you get the continuous state space model, okay, once you get this continuous state model, then we're going to use approach, okay, basically called discretization approach. Okay. And in this discretization approach, we'll be able to obtain, okay, a zero order hold equivalent discrete state space model. Okay. So this is this branch here. Okay. So you obtain the discrete space model through discretizing a continuous state space model. So we'll show you this one here later. Okay. Yeah. Is that good? So that's the the old bigger picture, basically how to obtain this discrete. So in the end of the day, for these two here, they should be equivalent. Okay, so no matter which direction that you go, the results should be the same. Okay. So I'll show you one very quick example. Let's say, how do we from here, given a difference equation, how to get a discrete state space model, right? So I'll show you one example right here. Okay. So just kind of imagine in your head that this difference equation somehow obtained through this g of z at here. Okay. Yeah. So here's a difference equation. It's like you're given a differential equation, right? And how do we get a discrete space model? Your first step is to choose state variable. Okay, the first step is always to choose state variables. This is a second order system, because there's a highest order difference. This is k plus 2, this is k, so it's a second order system. And you're actually going to be able to pick two states at here. Now, picking the state variables is I would say it's a tricky business. It's not a unique solution that you have to stick to one way to pick one here, right? But there are certain patterns you can follow here often in time. So we pick two at here. We'll pick the first state to be the same as this y of k, and then we pick our second state variable to be the y of k plus 1. Okay. So now this is y of k plus 1, which is basically this first state here is y of k. So you can see I can write the second state as x1 of k plus 1 here, right? Yeah. So x1 of k plus 1 is basically y of k plus 1. Okay. So with these two state variables, going back to the original difference equation. So this side here is y of k plus 2. So y of k plus 2 according to the selection of state, which is what? x2 of k plus 1, right? This is x2 of k plus 1. And then this u of k, just keep it there, that's your input. And then this 1.7 y of k plus 1 according to our selection state, which is x2 of k. And then last one here is y of k, which is x1 of k. Okay. So now the original difference equation is transformed, okay, into a completely different view now, using the selected state variables. So here is one equation, and here for x2 of k plus 1. And this is another one here. This is a x1, so this one here, x1 of k plus 1, then equal to x2 of k at here, right? So this x1 equal to x2. So you know what? I think I'm going to write this one on top of this. So x1 of k plus 1 equal to x2 of k. Okay. So yes.
Quick question: how are those two different states if it's the same? They're both representing y of k. Just one's at a later sample time.
Yeah.
Like why is that two different states, not just the same state?
Two different states. Yeah. So this is a difference equation, right? You might think this is so little difference at here, but they're completely different thing. One is y of k, and the other is y of k plus 1.
Wouldn't that represent one state just at an instant, one sampling time later, or is that not true?
Wouldn't that just represent one state later?
Like one sample?
Yes, technically speaking, yes. It is. This is just one. This is. They say this is the future of y of k. Okay.
Yeah.
This is the future. This is the current, and this is the next step. You see what I'm saying, right? Yeah. So I think you got to be careful here. You see, if you see, if I have a y of k plus 1. Then I can get y of k, right? You see what I'm saying? So if I have this number sequence here already, this is y of k plus 1. How do I get y of k? We just shift backward one step, isn't it, right? But this is the future, so you don't know the future yet. You see the point here? So if what you have is y of k, let's say, but you can't. When you have y of k, but then you're not going to be able to get a y of k plus 1. Yes.
Would it be different if it was y of k and y of k minus 1? Would they then be the same state, one delayed?
Yes. You could see that. Yeah. So when you have a difference equation, the way of writing, let's say, you can have this y of k at here. And equal to this plus y of k minus 1, and this, and y of k minus 2, right?
So
okay.
It was still two different states?
Well, then I would explain it's different now. If I write it this way here, right? If I write it this way, I say, now I have my past y of k plus 1, y of k minus 2 past, right? Then I can calculate my current y of k. You see what I'm saying, right? So the difference equation maybe is a little. Let me give you the maybe the differential equation. Let's see. Here's the differential equation, right? Yeah. So if you have a differential equation and you wanted to write it into a continuous state space model. And typically what we choose is we can choose, let's see, we can choose use x at here. Let's use a y here. Okay, different symbol here. So we can choose our first state as the position. Okay, and we can choose our second state as our velocity. Right? Yeah. So. And you can probably have a similar basic consideration here. What's the difference between the position and the velocity here, right? So this one here, actually, when you discretize one branch at here is to discretize a continuous one into the discrete one, right? Yeah. So if you have a continuous one in here, and when you discretize into the discrete state space model, you're going to end up with two discrete state variables. That two discrete state variables will look like basically y of k plus 1. They are actually still representing one is the position, one is the velocity. Okay? Yeah. Is that good? Right. So let's have a few exercises. I think there's always just a little probably adjustment to get used to the discrete basically domain here, right? Yeah, because we're always used to the continuous domain. When you see position velocity, it's very easy to understand, right? Yeah. Okay. So you see now the way I pick the state variable at here, we end up with two different equations describing the two state variables, and they are exactly in the format as the general format like this one here. Okay, the general format. Okay, one side is k plus 1, and the other side is k. Okay, so the next step is related to the current step. So these two equations, basically, you can rewrite these two equations using the linear, the LTI, the linear state space model now. So let's look at these two equations, how we can transform it, okay, into the state space model. Okay. So this is a single input, single output system right here. All right. Yeah. Here is the difference equation for the two state variables. Here is how I wanted to put it into the linear model format. Okay. Here is the A matrix, and this is the B matrix here. Okay, so let's look at the A matrix based on the two equations that are here. So what will be the A matrix? So x1 of k, right, equal to x2 of k. So basically x1 of k equal to the first row times this column here, right? Yeah. So the first row times this column will have to be 0, 1 in order to give you x1 of k at x1 of k here, and the b at here should be what? 0, right? Because the input u of k appears only in the x2 of k plus 1 expression. Second row at here, what's the second row? The coefficient for x1 of k is negative 0.72. The coefficient for x2 of k is 1.7, and then the u of k here is 1. Okay, yeah. So that's the state model, right? The discrete state space model for based on the regional difference equation right here. Okay, yeah. And then you should also have the output equation. So this I don't have the arrow sign here because it's a single output. The output just x1 of k, right? Just x1 of k here because of this definition of x1 of k. Then this is equal to x1 of k times x2 of k. Okay. So that's just 1, 0 at here. And then you have a 0 times u of k. So this is your D matrix, right? So this D matrix, just a 0. So that's a very simple example. When you have a difference equation, how you can derive the state space model. Okay. Good. So now I'm going to go into more detailed, basically, derivation now, okay, in terms of deriving state space model. But before we do that, there's one concept I wanted to cover it here. Okay, the concept to use is the simulation diagram, which will help us derive the state space model. So basically, how do we derive a simulation diagram from this given pulse transfer function? Let's say you have a pulse transfer function, and now we wanted to obtain this as a so-called simulation diagram. Okay, I'll show you what simulation diagram is. Okay, let's say, for example, here is a simple pulse transfer function. So this is a pulse transfer function here. And as a matter of fact, if you see this one, should probably remind you something from our previous lecture. So this one actually is a what? Is a it's the trapezoid or Tusting's method for numerically approximating the 1 over s, right? Okay, yeah. So to draw a simulation diagram, and often in time, what you have to do first is to rewrite this pulse transfer function into the z to the power of a negative coefficient format. Okay, so here what you do basically you divide z. Okay, divide z for both the numerator and the denominator. Then you'll be able to obtain the same. Okay, it's the same pulse transfer function, but now it's in the z to the power negative format now. Okay, yeah. The reason is because when we use the simulation diagram, we're gonna use a block, which is a z to the power of -1 block, for our simulation diagram. And z to the power -1, as we learned, physically, it basically represents what? Delay, right? Yeah. And delay, when you implement that in an actual system, right? When you implement that in an actual system, so this one here in an actual system, you can use one memory basically, right? To store the previous value, for example, right? Yeah. And then you can release that value on the next basically time instant. So that memory, and often in time we call it register, basically functions as this z to the power -1 block. Okay, yeah. So that's why we will single out this z to the power -1 block for our simulation diagram. So now here is your pulse transfer function. Okay, and then I'll transform the I'll convert this pulse transfer function into difference equation. Okay, so look at what the difference equation is. Okay, and it's very easy. So multiply the u of z with the denominator here, and then multiply e of z with the numerator here. Okay, so you get u of z times 1 minus -1 here, and that equal to e of z times 2 t over 2 1 plus this. Okay. So that's after multiplication, and then you can multiply the u of z into the bracket and multiply e of z into the bracket, and then you take the inverse z transform. Okay. And if you take the inverse z transform for both sides of the equation, here you get u of k, right? Here you get u of k here, and u of k this times z to the power -1 is 1 delay. Let me move it to the other side, so you get u of k minus 1 in here, okay. And then plus here is t over 2 e of k plus e of k minus 1. So that's a difference equation, right? So from pulse transfer function to difference equation. And this z to the power -1 comes in handy because that basically just represents a one-step delay at here. Okay. So once we're here, now we're ready to build our simulation diagram now using this block z to the power -1. So here's what you do. So looking at this, this is your current, basically this is your current output here, right? The current output value. Okay. The current output value are based on the previous output value plus the current input and the previous input. Okay? Yeah. So here is the simulation diagram. You start with the e of k at here. So here is e of k plus 1. So here you feed that into one junction and here, and this side give it to the z to the power -1. So you see this is your E of k, and the whatever passing through this z to the power -1 will be e to the power k minus 1, right? Yeah. So this is basically this portion here. So that coming out of this, right? And then multiply by a constant again, t over 2. And then in order to get the output at here, right? So let's say this is your output, u of k. Okay, this is your output of k. So your output u of k is the signal at here plus u of k minus 1. So basically, okay, so this is plus, plus, right? Now you get a simulation diagram. Okay, yeah. So the simulation diagram essentially is to realize this difference equation, right? Yeah. It's also very much like the logical flow when you're doing actual programming, right? So when you program, you know, in order to program to get this output here, you know, you had to program to program the addition of these two, and program the delay of this, and then plus this to get to the output here, right? Yeah. So sometimes you can also call it sort of programming diagram here. Okay. That's a simple example. Okay. The idea is once you get this simulation diagram, then we can derive our state space model by picking the state variables from the simulation diagram. Okay. So I'll show you that. Okay. Okay, so I'll write it down in here first. Once you get your simulation diagram, then what you do next is you choose state variables. Choose state variables from the the simulation diagram. And as you're going to see, we're going to actually pick state variables here and here. Okay. And basically to achieve the next step, and then one from here, and then you get your discrete state space model. Okay. All right. So now let's get into real business at here. Okay. And I'm going to write down a general pulse transfer function. Okay. General pulse transfer function. But I'll approach it using actual simple ones here, okay, instead of very complicated general expression. General basically means you have a numerator and you have a denominator, and we're gonna pick. My writing for the general is this, but I do need to warn you that different textbook or different from a different lecture notes, you may have a different representation. Okay. So here's a general format. So numerator divided by denominator, and everything is in the z to the power of a negative power format. Okay. Yeah. And I have a handout that given to you guys that kind of summarize the two common format: control canonical and observable canonical. They are based on this general formats added here. All right. Yeah. So I do get the feedback from previous year that you probably if you compare notes from this one with the notes from your motor control, you probably will see, well, how come they're different? The reason is because the symbols here, okay, they might different. So sometimes some textbooks start this one is a BN minus 1, backwards, okay. So the N plus, it's actually the same thing, but it just looks different, okay. Yeah. So here's a general one here. So the first case we're gonna look at is control canonical. So we'll look at results, a discrete state space model from the general format, end up with the so-called control canonical form. All right. Yeah. So I'll do this in using an example here. Okay. Okay, so let's look at this example here. Here's a given pulse transfer function g of z. And first step, okay, we will rewrite this pulse transfer function into this format, which is always in z to the power of negative, okay, powers. Okay. So what you do is basically you divide both the numerator and denominator by z to the power of 3. Okay. So your numerator will become 0.5, negative 1, and then z to the power negative 2, right? Yeah. And now the bottom here is 1 plus sorry, this is a square here, huh? Yeah. Okay. All right. That's now it's in the general format now. Okay, general form. So if I do a little comparison in here, so comparing this one with the general format here, what are these? What's the B naught value in this case? Yeah, that's right. So B naught is 0, and this is your B1, B2, right? Yeah. So at the bottom here, and this is your A1, A2, and A3. The reason I'm doing this is because, you know, for the future or for your own work, you don't have to derive every time, right? And you have your formula, and you can use your formula. But of course, sometimes I do ask you to derive to solve a question. But in that case, you have to derive, okay? But otherwise, you can always use the formula to compare the coefficients. Then you can put it into the matrix, okay? Yeah. And the other thing I want to emphasize here, we're going to come back to this. The degree of a numerator at here is 2, and the degree of the denominator at here is 3. Okay? Yeah. So the degree of the denominator in this case is bigger than the numerator. And that's typically what we want. Okay? I'll explain this later. Okay, but let's just for now just a side note. Okay, once we have this now, to derive the control canonical form, so we introduce a temporary symbol. Okay, we call that h of z. Okay, so introduce an h of z at here. You know, we're not changing it, just basically introduce that both at the same time in the numerator and the denominator, so they cancel each other, right? Okay. And then I'll let the y of z over h of z equal the numerator. Okay, so equal this 0.5 and this. Okay. And also we let the h of z over the u of z equal to the bottom, the denominator, so that's equal to 1 over 1 plus So nothing changed, just, you know, what does it look like with this newly introduced h of z at here. So now I can, if I look at this one here, I see, okay, so y of z, based on the first expression, equal to 0.5 times this, and this times this. Okay. And then this part right here is h of z equal to, so this portion in here, you do the same thing. H of z times this numerator here, okay, times the numerator, denominator, yeah, equal to u of z times 1, right? Yeah. And then I will just keep the h of z on the left side and move the other terms, okay, to the right side there. So that basically equal to pardon me, this one, u of z. So this portion is from down here.
Multiplied by h of z.
Yeah, so h of z multiplied by this, h of z multiplied by this, right?
Is equal to u of z.
Yeah, I'll write the u of z at the end. Huh? I'm moving things around. Yeah. Okay, let me not skip steps then. Okay, so h of z times 1 plus h of z plus the whole thing equal to what? U of z, right? Yeah. And then I will just keep h of z, this one here, and then move this the other term to the same side as u of z. Good? Yeah. Okay, so basically we end up with two expressions like this, okay? Two expressions like this. Okay, so from here, now I'm actually ready to build this simulation diagram, okay? So let's see how I can build the simulation diagram. So remember, input is u of z, okay? The input is u. Yeah. I want to go down up a little bit. Here is your input here, okay? Here's input, and output is over here, y. Okay? Or you can call it y of k or u of k, that's okay. Right? Yeah. Good? Yeah. So let's start from the second one here, okay? This h of z equal to this plus minus plus, and then plus u of z, right? Yeah. Okay. So let's say we have a hypothetical value h of z, okay, somewhere here. Okay, this is your signal h of z here, right? Yeah. So the first step is this h of z. In order to multiply this 0.6, we had to let it pass through what? One step delay, right? One step delay. Once this is passed through this now, from here we can use it and then multiply by negative 0.6, right? Yeah. Okay. Is that good? Yeah. And then the next one in here, right? The next one is h of z times z to the power negative 2. So that basically means you keep letting the same signal here to pass through it. Another delay here, okay? And then whatever coming out of here, and you can use it and multiply by negative 0.5. Okay? So that'll give you this chunk right here, right? This chunk. And another one here, you let it pass through another delay at here or register. So the output of this block, and you can multiply with negative 0.3. Okay? Yeah. Is that good? Yeah. So now we can put things together. So you see this one plus this plus this plus this plus u over z. So I can form a junction at here. Okay. There, right? So u over z plus this plus this plus this, and that's your h over z basically. Okay, here's your h over z here. Is that good? Yeah. So that solved this portion here, right? Solve this portion. And now let's go back to this y over z at here, right? And y over z equal to what? Equal to 0.5 times z to the power negative 1 h over z. And z to the power negative 1 h over z, where is that signal? It's here, right? It's this. Okay? It's at this location. So we can use it and then multiply by 0.5. Okay? Yeah. And then you have another one, z to the power negative 1 h over z, so which is at this location. Of course, the in front of it is 1. And then you add these two. You add these two up. And you get your output of y over z. Okay? Yeah. So now this is your basically the so-called simulation diagram in here. Okay? Yeah.
And so you don't connect the rest.
No, you don't need to, right? Yeah, you see, this is exactly a description of the original system, right? Yeah. Good. So as a matter of fact, if you're going to build a circuit, right? And this is essentially how you would build a circuit now. You will have a 3 register at here, and somehow you have a gains go through certain means, and you build your circuits to realize this input-output relationship, right? Yeah. Is that good? Yeah.
Would that work with like flip-flops?
Yeah. Yeah. So that's basically how you would use it as a register, right? Yeah. Yeah. Good. So from here, the idea is we want to build our discrete state space model. So from here, based on this simulation model here, how do we pick our state variables now, right? So then the next step here is to picking state variable. Okay, picking state variables. So here's how you pick the state variables here. Okay, we pick state variables. There are actually different ways of picking it. We're picking state variables right after the register. So you look at this one here. How many registers do we have? 1, 2, 3, right? So you pick the state variables right at the locations, right after the register, which is where? Here, 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 right? Yeah. So we're going to call this one here, we're going to call this is our first state, x1 of k. Okay, so this is that signal over there. I call it the state variable x1 of k. Okay? So this signal right here is our first state. And this one here, I'm going to call it the second state variable. So which is what? x2 of k, right? Okay, at this location. And then here is x3 of k. So 3 state variables. Good? Yeah. And once you get the state variable now, and then if you look at the state variable here, this is your x1 of k here. This is your x2 of k. But technically speaking, this location can be also called what? x1 of k plus 1, right? Because this is a 1 delay. So the x1 k plus 1 delay by 1, you get x1 of k, right? The same thing at this location, this is also x2 k plus 1. Okay? Yeah. Clear? Good. So similarly, before this block at here, at this location, this is x3 of k, so at this location this is basically x3 of k plus 1. Okay, yeah. So now I'm ready to write down the difference equations for each one of the state variables now, right? So by looking at this simulation diagram, right? So basically from simulation diagram, okay, from simulation diagram, let's look at our state variable equations. First, let's look at the first one. What is x1 of k plus 1? So here is x1 of k plus 1, right? x1 of k plus 1 equal to, it's a function of the other state variables and control signals. And in this case here, you look at x1 of k plus 1. It's nothing else but the same as what? x2 of k. So that's your x1 of k plus 1. And then your x2 of k plus 1, which is this location here. And that just x3 of k, right? Just x3 of k. x3 of k plus 1. Okay, this one is a little complicated now. So x3 of k plus 1 is at this location. So now you can probably, let's say, you can tell me now, what does x3 of k plus 1 equal to? Input plus this, right? Yeah. So maybe let's just write down the obvious one here. It's plus u of k for sure, right? Yeah. So what's the signal over here, right? The signal over here, what is that? That's what? Negative 0.6 times, that's right, times x3 of k, right? Not x2 of k plus 1, because you're writing the state space equation, right? So it's negative 0.6 multiplied by x3 of k, and then keep going for the other one, negative 0.5 times x2 of k, negative 0.3 times x1 of k. Yeah, I should probably reverse it, but that's fine. Yeah. Right.
So that's for our
Yeah. See, this is exactly the format, k plus 1 format on the one side, and everything else is k, right? Yeah. So, next step, guess what? You will put everything into a matrix format now. Okay. So this is your next step, and you can try yourself. So here is the state variable equation for each individually, and how do you put it into a matrix format? 0, yeah. Next one. That's right. Yeah. So the last row, just be careful because I wrote it like a reverse order here, so it should be here's 0, 0, 1. Okay. Good. For the last row at here. This is basically negative A3, negative A2, negative A1. Okay. And this is, of course, your A matrix. This is your B matrix, right? Yeah. And don't forget the output equation. Okay. So we have our output equation right here. Okay. You can also get output equation, same thing. You can also get it from the simulation diagram. So if you look at the output equation, that's equal to what? 0.5 times x3 plus 1 times x2. So if we write it into matrix format, and this is 0, 1.5. And 0.1.5, here is B3, here's B2, here's B1. Okay. And this is the so-called control canonical format. Okay. And there's a reason why it's called the control canonical format. Because later, when we derive the pole placement, there's this, so basically the idea of controllable and observable concept. And in order to determine whether it's controllable, if you have this control canonical format, then you can immediately basically tell whether it's controllable or not, basically. Okay. Yeah. Okay. So just comments at here. This is actually something I mentioned, but I didn't really answer that. Let's say you have your pulse transfer function given, okay, in the numerator divided by the denominator format. And I did mention that actually just from this example, what we typically have is the degree of the numerator is less than the degree of the denominator. Okay? Yeah. So let's take a look at a special case at here, right? Take a look at special case. If the degree of the numerator is actually the same as the degree of the denominator, okay? Yeah. Then what does that mean, basically? Okay. So if this degree is the same thing, so for example, in this case here, if I wanted to write it back into the difference equation, so this is what you do, right? You multiply the numerator with the u, multiply the denominator with the y. Okay? Yeah. So in this case, if the degrees of the numerator and denominator are the same, and then I don't know how the same basically means, maybe z squared plus something at the top, and also z squared plus something at the bottom here, right? Yeah. And then when you multiply the y with the bottom, and the n, and the u with the top put over here, okay? And then you take the inverse z transform. So what you probably will get is y of k on one side here, for example, okay? And the other side is also u of k on the other side over here, right? That makes sense? Yeah. So now you can see your y of k is, and this side here maybe 3y of k minus 1, I don't know, right? Yeah, like this, okay? Yeah. So now you can see your output y of k directly depends on what? Depends on the previous input, and you may have, let's say, u of k minus 1. It also depends on the previous output, and also depends on this one here is what? The present input, right? So basically your current output depends on the past input, current input, and also past output value. Okay? Right? That makes sense, right? Yeah. However, right, if you think about it, if you think about the case set here, if you think about the case that the degree of the numerator is actually greater than the degree of the denominator, okay? So, for example, right, let's see, just for this example here, okay? Yeah. And you use this divided by this. You typically what you're going to get here is you're going to get the z plus something like this, okay? Yeah. Because the degree here is greater than the degree of the denominator here. So when you divide this top, the bottom here, so let's see if this is here. So what do we get here? So that's z. There should be z squared plus z. How do I get? Yeah, this should be 1 here, right? This should be 1. Okay, that makes sense, right? Okay. Then now, if you multiply the y of z to do this equal thing in here, right? So basically, if you do this here, so y over z multiplied by this, and then u over z multiplied by this. Okay, yeah. Is that good? And let's divide it by z cube on both sides at here. Okay, let's divide by z cube on both sides. Okay. Let's divide it by z, just a z here, z square here. Okay, divided by z square. So we get y over z and 1 plus z negative 2, and then u over z, z plus 1, z plus negative 1 plus z negative 2. Okay. That makes sense, right? So now I take the inverse z transform. What do we get? Y of k equal to y of k minus 2 plus, here is, what's this one here? U of what? K plus 1, exactly. Okay? Yeah. Negative. Okay. So this is a case when the degree in the numerator is greater than the degree the denominator. So why is it so abnormal now? So your current output depends on the past output value, and also depends on what? The future, right? And when this thing happens, this is a system, remember, what do we call that? It's called a non-causal system, right? And that it basically means it's not realizable, right? Yeah. So, which is why we typically have these conditions, okay, given. And if you look at the general format, in my case, general format, this is basically, in the extreme case, the degree numerator is same as degree negative. Okay. Okay. So any questions? And then we'll look at the observable one in the next lecture. Okay. Yeah. Okay. Sure.